Hello, welcome to Digital Gravity Lab. I'm Matthew Rissler. I am a PhD student in the Computational Sciences and Engineering program at Harrisburg University. So this is another one of my assignments, and we don't have much time to run through, so I'll jump right in. So this assignment is on pattern taxonomy design space. So if you're asking what that is, pattern taxonomy is a classification of formulas codes to common computational problems, while a design space is the range of possible solutions within a problem domain. So to bring that down to make sense, for this one I've got two assignments: a heat diffusion, an n-body short range, which I've selected to use for this assignment. And so looking at pattern taxonomy, that would be a map and reduce for the n-body. So what that does is each particle is mapping the force function across all the other particles, and then it's reducing those contributions to one net force. So a map and reduce versus a stencil for heat diffusion, which is basically looking at each new cell values depend on its local neighbors. And the design space there are things like using CPU versus GPU, figuring out the memory layout, the block size, how many threads there are, the boundary conditions, and things like that. And so looking at heat diffusion, that is the modeling and simulation of how heat spreads over time across flat two-dimensional surface. And as I said, it uses stencil, a 5-point stencil where radius is 1, so it's looking at the center point and the 4 points around it. If you were looking at a radius of 2, you'd be a 9-point stencil, where you'd include all the ones right around it, that stencil around the center point, where every single point then is solving that, and you're going to be bouncing it from that one point, moving over to the next side, and bouncing back and forth and solving it. So the code here, I ran across GPU and CPU. So you can see here the code here, up, down, left, right, along with the center that's calculating for that point. Just to kind of see what that looks like. So depending on the size of the dot you're starting with and how many pixels you're using, and how many steps will kind of determine how that ends up looking in the end. But as you add a larger grid size, the time does go up a lot. With a CPU single core, the seconds per step drastically increases as the size increases. But you can see here in the bottom, didn't even start testing the core at the GPU with how many cores it has, even a grid size of 2000. So very nice there. And let's keep jumping down. As you're changing the radius and things like that, you can see that the time for each run increases. And so you can see here, and as you increase grid size, of course the size continues to increase. There's a bunch of overhead time for this first run at 250. And depending on the radius, you can see with much higher radius, it tends to take more time. But it's not necessarily consistent across every different version here. And then in the design space, bandwidth, right? If you're looking at native versus tiled memory versus temporal blocked, there's a lot less bandwidth having to go, more data reuse depending on what's picked there. Jumping to the next task there, the n-body short range. that's model that predicts motion of a system by calculating force and interaction between each pair or dozens, between all the different bodies. But it's grabbing that first one and then reducing it down to a single calculation for every point. So NJIT CPU version versus a GPU CUDA JIT. So this is running on a GPU, and then outputting differences between those. They do give slightly different versions across CPU and GPU. Trying to figure out why that is, but it does give a slightly different value. Most likely rounding errors. Particle counts going from 10,000 to 100,000 here. A small cutoff, so it is just looking ones right around it in this case, and looking at every single particle, just testing all the ones right around it. You can see the time, because that cutoff is so small, there's only going to be a few around each one. The GPU time is much less than CPU time, even for 10,000 particles. 200,000, you can see the GPU time even being more efficient. But single timestamp there for that. You can see that the GPU, the whole log scale, 17 times faster. Very nice there. Ran this a number of different ways, which we don't have too much time to get into, but did this graph here showing the different velocities. It's limited on how many it shows. It's not showing every one. The longer ones faster. Originally when I was running this, I didn't have any dampening, so they would basically bump into each other and then fly off in different directions, and things which would greatly add to a lot of the noise. Or if you started at an initial point, after 5 steps, you can see massively scattering in all different directions. But for running these, various dots, similar thing. GPU is much faster. I think it was a fluke with the first one, but 130 times faster, but it was averaging about 15 times faster across the different points here. So just had various different versions. This one across a different timestamp, very small timestamp. It didn't seem to move very much. Having its forces right at first, but then they all kind of collapsed into this center point here. This version 2 build here, just some testing, making sure CUDA was available. There were some various auto tuning launching. We did 2,000 points, 200 steps, time. What I actually did is I'll show it a GIF that I built out of this, and then look at timing as well across the two, so you can see CPU, GPU, looking at a speed up of 3 times at 2,000 points. The more points you had, the larger the speed up for GPU, because of some of that overhead cost per step in particular. And I'll grab some of those graphs in a second. But this last version I added in some dampening to it. So we'll scroll down, look at where we put that in here. But you can see I just did a full 1080p here. There we go, gamma 0.03. So let's look at what that looks like here. But then I did that across CPU and GPU, and then computed that across. So at 500, the GPU is actually taking longer. But then when you got into 5,000, it started being four times faster. So let's look at this, some of these GIFs before we jump here. But let's just look at this one in particular here. So this is 600 steps, 500 particles, timestamp 0.05, and with dampening, which also adds them when they crash together, they don't just go flying off. And there you go, they kind of collapse there in the middle, versus some of the other versions which I did here. We'll jump that one in here. You can see these same timestamp, but it starts just a little bit slower here. The other one, I believe I had a gravity of 2. This one should be gravity of 1. Didn't write all the notes and everything, but you can see them slowly jump in here, and then they collapse into the middle here and scatter because there's no dampening. So everything just kind of flies away, and you'll kind of see them collapse back, be attracted back in. But yeah, it stays very chaotic and messy without any dampening. So that is this assignment. I hope you enjoyed it. Let me know if you have any comments or notes. Otherwise, subscribe. Thank you.